parameter systems and distributed parameter systems. Now, to give a brief description about a lump parameter system, let us consider a short transmission line. In the case of a short transmission line, we are having a transmission line which is a short transmission. We supply a voltage, sending in voltage, and at the receiving end we get a voltage which is V of S, V of R, that is the receiving end voltage. Now, it will be seen that the voltage V of R, that is the receiving end voltage, will not be equal to the sending end voltage because there will be drop along the transmission lines. Now, in order to account for loss, what we do is we actually model the transmission line with just one inductor and a series resistor, and then we put a capacitor. Sometimes the capacitor is actually divided into two, and it is actually put on either ends, that is on the sending. We actually put the half capacitance value at the sending end and the other half at the receiving end. This is how the transmission line is modeled. So we have total capacitor is C. So one of the capacitor is modeled on the sending end, and the other half is modeled or is placed at the receiving end. So this type of this is known as a lumped parameter because there will be inductance throughout the line, and throughout the line, what we do is we consider the total inductance as just one single inductance. That is the reason why we call it as a lumped parameter. Now, in the case of a long transmission, see, this is a short transmission line. So in the case of long transmission line, and this is for this kind of a representation is known as a lump parameter. So this entire thing is actually can be represented with a mathematical model, and when we apply V of S to the mathematical model, that is the input x of t, we can consider this to be an x of t, and we get an y of t at the output, which is VR. Now in the case of a long transmission line, the inductance, the resistance all along the line is not lumped as one parameter, but it is distributed along the line. Say we have a resistor, like an inductor, then we have an inductor, then again a resistor, inductor. So it is distributed. Similarly, the capacitor is also distributed. So you have this. So we have a VFS, and then we get RFS. Now, so this entire the distributed parameter system can be modeled with as a mathematical equation, and to the mathematical equation, if I apply x of t, which is v of s, I get y of t, which is v of r. That is the receiving end voltage. So this is another type of classification where the transmission line can be represented either as lump parameter system or a distributed, depending on whether it is a short transmission line or long transmission line. So this is our second classification. We go to the next classification, which is known as the static and dynamic systems. Static systems, dynamic systems. Dynamic systems. Now, in the case of a static system, it does not have any memory, so it is memoryless. whereas the dynamic system has memory, so it can be considered to be a memory. So to give an example, let us consider y of n, that is a discrete time system. It's nothing but n times x of n. Now you can very well notice that x of n, y of n is dependent just on x of n, and that too it is dependent only on the present value. It's not dependent on the future value, or it is not dependent on the past values of the input. So a system which is just dependent, the output is dependent only on the present value of the input. Such a memory is known as a static system. So let us say what is a dynamic system. Suppose if I am having d t is equal to, sorry, let me take example, x of t, y of t is differentiation of x of t minus divided by dt. Now this actually we can mathematically we can represent it as x t plus some small increment. This is the future value of the input, okay, minus x of t, the present value of the input, divided by delta t, that we have a limit delta t tending to 0. Now this is the definition of d over dt of x of t. Now you can very well see that y of t is dependent on future value of the input. Now when y of t is dependent on the future value of the input, such a system is known as a dynamic system. So we can take another example also, say y of n minus y of is equal to x of n, or we can write it as, let us write it in terms of x of n. So y of n is equal to x of n minus x of n minus 1. Now y of n is dependent on the past value of the input. So this system is a dynamic system. Okay. So again another example, at y of t is equal to x t minus 2. Now this is a dynamic system because it is dependent on the past value, not on the current value of the input. So when a system whose output is dependent on the past values and also on the future values, then such a system is a dynamic system. Whereas a system which is dependent only on the present value, then such a system is known as a static or memoryless system. And dynamic systems are also called a system which has memory system, a system which has memory. Okay, so let us take another classification which I can, a linear system, linear and non-linear systems. Now what is meant by a linear system? Suppose if I am having a system which has a system function, and to which I give a input x of t, I get a value out of y of t, or maybe I give a input x1 of t, then I get y1 of t. Then to the same system I give another input which is x2 of t, and I get an output which is y2 of t. Now I can, instead of writing like this, what I can say is the system is the following property, that when I send an input x1 of t, I get the same input out, which is y1 of t. It doesn't do anything, it just actually transmits the input to the output. Okay, let us say this is y2 of t. Let us say when I add both the inputs and I feed it into the transformation block, then what happens? I get whatever goes in just comes out. So this I can say it is y1 of t plus y2 of t. such when the output when the inputs when separately given into the system, we get separate outputs. When both the inputs are added to the system and when we pass it through the transformation block, we get an output which is nothing but the sum of both the outputs that we have previously got. That is y1 of t plus y2 of t. Now such a system is known as a linear system. Then what is a non-linear system? Now this linear system will become clear once we discuss the non-linear system. Suppose I have another transformation block. I'm going to discuss non-linear system now. Let us say I am having a transformation block. A transformation block, what it does is it takes the input and it just squares it up, and it is given as the output. Now, to the same transformation block, I feed another input which is x2 of t, and I get an output that is x2 squared of t, which is equal to y2 of t. Now what I do is I add up both the inputs and then send it through the transformation block. When I do it, I get an output which is something like this: x1 of t plus x2 of t squared, which is not something like this: x1 square of t plus x2 squared of, which is this part is actually y1 of t plus y2 of t. So the y we got here, the y1 of t, is actually not equal to, it is not the sum of both the outputs that we got previously when the inputs were separately passed through the block. Okay. Now this is clearly a non-linear system. So a linear system is one where if we add up the inputs and then when we add up the inputs and pass through the transformation block, we get an output which is nothing but the sum of the outputs that we would have got if the inputs were separately passed to the transformation block. Otherwise, such a system is a non-linear system. Okay. So now let us see yet another classification which is known as the stable system and unstable system. A stable and an unstable system. A system is said to be stable. Otherwise, more specifically, it is known as BIBO stable. A system is said to be BI, that is bounded input, bounded output. If I, through a transformation block, I pass a bounded input, an input which is within certain limits, which is finite limit, I get an output which is again within the finite limit. So if the transformation block produces an output which is within a finite limit, provided I have passed an input which is within the finite block, within the finite limits, then such a system is known as a BIBO stable. Otherwise, it is known as an unstable system. So to give an example, let us say we are having y of t cos x of t. We know that a cos function varies between a cos function varies between 1 and varies between 1 and minus 1. That is, its output is always bounded. So suppose if I pass a bounded input, then definitely I am sure that I am going to get a finite value if it is passed to as the argument of the function. Then definitely I am sure it is going to have a finite value. The output is going to be of finite nature. So such a system is known as a BIBO stable. So okay, this otherwise the system is, if a bounded input provides an unbounded in, then such a system is known as such a system is known as To give an illustration, it's not as an unstable system. Let us for instance y of t is equal to tan of x of t. So if suppose x of t happens to be 90 degrees, then the output will become unbounded. So such a system is unstable. So so we have seen what is meant by a stable system and what is meant by unstable. To summarize, suppose I have x of t which is having an upper bound and a lower bound. Suppose the signal is actually varies only between these two values, and if I give the system give this uh, as the input to the system, then the output also will have to be of a similar nature. So it will be something like this. Okay, so it's not exactly not a sine wave, but it can be need not necessarily be a sine wave. Okay, so it can be of any shape, but it has to be within the bounds. That is what is meant by a, let's say we are having some, but it is lying within a bound. So this is y of t. So this um, is what is meant by a stable system. So next let us take up another classification, which is known as time varying systems and time invariant systems. So what is meant by a time invariant system? Time varying and time. Suppose you have a transformation block and to which I have applied an input, I get an output x of t. So x of t I have applied and I get an output which is y of t. Now what I have done is I have shifted the input. Let us say I have shifted the input, and then I have time shifted the input and then I given it to the transformation block. I will get another. I get an output. Let me not. I get an output which is t comma tau. Okay. Now what I do is I take the y of t. I take this y of t and shift it. Then when when after shifting, when this becomes equal to this, then we can say it is a time invariant system. Otherwise, the system, if when this is not equal, then such a system is known as a time varying system. So for a time invariant system, the y of t comma tau should be equal to y of t minus tau. The y of t minus tau is got by taking y of t and then shifting it by a tau units of time. So to illustrate this, let us take an example. So let us say y of n is equal to x of n plus x of n minus 1. So this kind of a dynamic system. But we have to do the first operation, that is when you pass the input. Suppose I pass an input, that is x of n, to the transformation block, I get y of n, and that y of n is nothing but x of n plus x of n minus 1. Now next what I do is I pass a time shifted input and I get an output which is y of n comma k. So this will be x of n minus k plus x of n minus k minus 1. Fine. Now what I have to do is I have to take this one, that is y of n, which is x of n plus x of n minus 1, and I have to do a time shift by k units. So when I do it, I get x of minus 1. So we can see that this and this are equal, that is x of is equal to x of n minus k. So this is essentially a time invariant system. So my conclusion is this is a so this is a time invariant system. So let us illustrate time varying system then. Let us take an example. Let us say y of n is equal to x of 2n. Now when you pass an input, let us say we have the transformation block, and when you pass x of n, I get y of n, which is nothing but x of 2n. Now what I have to do is I have to pass a time shifted input to the block. I get an output which is nothing. I get an output which is nothing but n comma k, that is nothing but 2 minus k. Now what I do is I take y of n and I shift this by, which is nothing but x of 2 times n minus k. Now you can observe this and this, both are not equal. So y of n minus k is not equal to y of n minus k. So this is this is a time varying, yeah, it's a time varying system. So this is what our conclusion is. So let us take up another classification, which is nothing but causal and non-causal systems. Causal and non-causal systems. So a causal system is one which is one whose output depends only on present and past values of input and past values of output. Not on the future value. Not when on the future values. Such a system is known as a causal system. A non-causal system is if a system is dependent on the future values, then the system is a non-causal system. If the output depends on future values, then such a system of input, then such a system is then this is non-causal systems. Okay, causal system. So this is the definition for. Let us take a few examples of causal system. Suppose y of n is equal to x of n plus x of n minus 1. Here you can very clearly see it is dependent only on the present value of the input and the past value of the input. Suppose if it is like this, x of n plus x of n plus 1, then in that case it depends on the future values of the input. Then this system is non-causal, whereas this system is causal. Let us say we have a system y of t is equal to x of root of t. Now if you substitute t is equal to 0.36, let us say let us substitute this value and see y of is equal to x of root of 0.36. Now this becomes y of 36 is equal to x of 0.3. Now if you draw the graph, let us say 0.36 is here, whereas 0.6 is here. So the output here is dependent on the input on the at 0.6, which is it is dependent on the future value of input. So this system is clearly non-causal. Let us take it another example. Let us say we are having y of n is equal to n squared. Let us say we put 0.1. Let us say we put 2. This will become 4. So it is dependent on the future value. So the system is non-causal. What about this? Y of t is equal to x of t minus 2. So this is x of t plus x of 2 minus t. Let us take the example x of t minus 2 plus x of 2 minus t. Now if you substitute, let us say 1, that is y of 1 is equal to x of minus 1 plus x of 1. Here it appears as if the input, the output is dependent only on the present value of the input and the past value. Suppose if we were to substitute minus 1, say minus 1 is equal to x of minus 3 plus x of 3. Now the present value is negative 1. The negative 1, the output at negative 1 is dependent on the input at t is equal to 3, which is clearly it is depending on the future value of the input. So this system is essentially a non-causal in nature. So we have discussed elaborately various types of systems. So summarizing what all we have discussed in this video. We have given an introduction to the systems. So under introduction, we first touched upon what is meant by a system. It is a transformation block which transforms an input into an output. So next was classification of the systems. So under classification, system classification, We have seen what is meant by continuous time systems, where the input is continuous in nature and also the output is continuous in nature. And then what is meant by discrete time system, where the input is discrete in nature and output is also discrete in nature. Then we saw what is meant by a lumped parameter and distributed parameter system. And distributed parameter system. Then we saw what is meant by static and dynamic system, or otherwise memory and memoryless and dynamic. That which has memory systems. Then we saw what is meant by a linear system, linear and non-linear system. Then we saw stable systems and unstable systems. In fact, we saw first we saw the stable system and unstable systems, and then we saw the linear and non-linear systems. Stable systems. Then we saw what is meant by time varying, and time invariant. Systems. And finally we saw what is meant by causal and non-causal systems and non-causal systems. So that is all we saw in this video. So next we will take up Fourier series analysis for continuous time signals. Thank you.